We sometimes forget how much animal behavior depends on the rhythms created by the sun. By governing the seasons, the sun provides yearly cycles of growth and reproduction. The sun also provides times of activity and times of rest. The moon controls the rhythm of the oceans by raising and lowering the tides. But animals have their own sense of time that works in partnership with the cosmic forces. Their inner time is never wrong, which is the mystery of animal clocks. Animal clocks are designed to respond to nature's rhythms. There is first of all the stately pace of the seasons. Winter grudgingly gives way to spring. Animals don't become active before spring, and yet their clocks tell them it's coming. Coaxed by the rising temperatures, a new round of growth gets underway. Animal clocks also respond to the daily cycle with its changing periods of light and dark. The flowering of plants is actually due more to the lengthening daylight than it is the warmer weather. For animals, the summer is a time of contentment. Yet even before summer ends, they receive an internal signal to prepare for winter. As the colors of the natural world swell and fade, the days continue to shorten. The seasonal cycle and the daily cycle impose an unyielding rhythm to which animals must adapt or perish. This is why animals have developed their own timers, animal clocks. Forewarned, they can anticipate these external changes in nature. The Arizona desert is a good place to study animal clocks because the scorching days and chilly nights enforce a rigorous daily cycle. It is mid-morning, and already the rising temperatures are making this tortoise uncomfortable. In spite of their successful adjustment to the desert habitat, almost none of the creatures here can tolerate the sun after midday. This is the regal horned lizard. It is protected by its camouflage and by the bristling spines around its neck, which serve as a warning to snakes that this creature is difficult to swallow. The lizard cools itself by breathing hard, like a dog on a hot afternoon. The grinning face of the chuckwalla, one of the larger desert lizards. By this time of day, it can stalk insects for only brief periods before retreating to the shade. Most of the animals here sleep during the day, leaving the hot scrub to the lizards, birds, and giant saguaro cactus. But when the sun sets, the temperature falls dramatically, from 110 to 75 and down into the low 50s. The night creatures emerge, coyotes snuffling and barking in preparation for the evening's hunt. From their hiding places beneath the shadowy desert floor come spiders, pack rats, and rattlesnakes. A full night of activity passes. In the desert and elsewhere, the day-night cycle allows nature to get double use out of the environment. There are, in effect, two shifts of animals, and each is designed to operate best while the other sleeps. But because the desert heat is so unbearable, the daytime animals are at a disadvantage. They have fewer hours to look for food, and for this reason they must be active as soon as it's light. The horned lizard burrows out of the cold sand to meet the day, but the light cannot have penetrated the sand. How did it know to come out at precisely the right time? A desert iguana appears at the very same moment. It needs the sun to warm it into activity. And simultaneously, a leopard lizard. All three of these lizards were cued by the same internal device, an animal clock, synchronized exactly to the sunrise. There are other creatures in the Southwest whose cycles of activity depend upon animal clocks. For example, resting inside the limestone caves of New Mexico are great congregations of the world's only flying mammal, the bat. These bats spend their days sound asleep in total darkness. If artificial lights are turned on them, they tremble and squeak like half-awake puppies. It could be argued that they're as cute as puppies, too, until they open their mouths. These bats are insect eaters. They have the nocturnal functions of birds. Again, nature is operating efficiently, because if both bats and birds were active at the same time, they would have to compete for food. Cut off from light, the bats use animal clocks to tell them when the day is over. Even on dark and cloudy days, the bats leave their roosts every evening at sunset. At a point which can be predicted nearly to the minute, they pour out of the cave in waves. These are Mexican free-tail bats in slow motion. 1 million or more may live in a single cave. Over the period of a summer, the bats reset their daily clocks. They leave slightly earlier each evening to take advantage of the lengthening nights. In a moment, we'll see the working of even more sophisticated animal clocks. The first clues about animal clocks came from plants. Flowers which respond to the day by opening their petals were put in dark closets. Without any sign of daylight, they opened their petals at the usual time. Bees provided the next clues. 50 years ago, it was discovered that bees could tell time. If their feeding dishes were filled at 10 in the morning, the bees would learn to appear exactly at 10. Now we know that a bee visits a flower at precisely the time of day when the flower is releasing its nectar. What's more, a bee's clock works just as accurately in a laboratory when light and temperature are kept constant. In order to find the right flower at the right time, bees use the sun for direction. The discovery that animals navigate by the sun was an important one because it proved the existence of animal clocks. The breakthrough came 20 years ago in experiments with migrating birds. These are Canada geese, flying south in their characteristic V formations. For a long time, people wondered how birds could find their way year after year to the same winter range, sometimes over a distance of thousands of miles. Cruising at an average speed of 50 miles an hour, the geese travel 200 to 300 miles a day. In the evenings, they land in great numbers at regular way stations. Even young birds, which have never made the trip before, know the way south. theory used to be that the Earth's magnetic fields somehow guide the birds. Then a German scientist proved that migrating birds plot their course against the sun. Navigation of this kind requires a sure knowledge of time, because the sun is in a different position every hour. The ability of birds to migrate depends on their ability to measure time. In the last 20 years, a great number of animals have been shown to have biological clocks. The field mouse, for instance. In the course of a day, the mouse has specific periods of activity and specific periods of rest. Put the mouse in a cage with a treadmill, and it will maintain the same cycle. Even in constant light or dark, the cycle still applies. The mouse runs on the treadmill and rests just the same, according to its internal clock. But when a mouse is cut off from the rhythms of a natural day, its own day no longer measures 24 hours. Instead, the mouse creates a slightly longer or shorter day, and it will run and rest to the new schedule indefinitely. Most animals, man included, demonstrate these independent internal rhythms. Even among frogs and toads, biological clocks are well developed. These are spring peepers, chirping their familiar song like a chorus of tiny bagpipes. Of all the frogs and toads around a given pond, the peepers are the first to become active in the spring. Although the exact time of their mating and singing may vary, it is certain that the spring peepers will precede the American toads, for example. Toads and peepers have different settings on their biological clocks. The young green heron, which feeds on frogs and toads, is able to change its menu every 2 weeks as each succeeding clock awakens a new species. The green frog comes out after the spring peeper, but before the toad. Recent experiments have shown that frogs have a sense of direction. Like birds, they get their orientation from the sun or the stars. Again, that calls for an intricate animal clock. Mallard ducks recently arrived from their spring migration, court each other in preparation for mating. The mating urges of ducks are directly related to the lengthening of daylight in the spring. The longer days swell their sex glands and make them restless. But the duck's biological clock is also involved. It's been shown that even in conditions of constant light, a duck feels the urge to mate at the same time in the spring. In spite of all the evidence about animal clocks, the location of the clock has never been pinpointed. It may be in the brain, or in the hormone glands, or even in the genetic pattern of individual cells. All that can be said for sure is that the clocks work. These ducklings, for example, hatch and leave the nest at just the same time as the hatching of certain insects in the water. The ducklings rely on these insects to make it through their first few weeks in life. Sometimes two clocks, each with a different setting, are at work within one animal. More about that in a moment. Along every ocean coast is a strip of land known as the intertidal zone, the area between the high and low tides. The creatures here lead a double life, alternately battered by the sea and exposed in the air. Limpets, for example, snail-like animals that brace for each wave by clamping themselves to the rocks. Instead of the daily cycle, it is the tidal cycle which regulates these animals. High tide is their active period. Barnacles emerge to comb the water for drifting nutrients. The animal is actually head down in its shell. Its feathery legs draw the food down toward its mouth. As the tide rises on the rocks, fresh seawater revives the animals resting in the tidal pools. The sea urchins now begin to move. The suction cups at the ends of their delicate feet feed the mouth at the center. An anemone waves its stinging tentacles, hoping to stun an unwary minnow and draw it into its gullet. The nudibranch, or sea slug, can attack the anemone without being stung. For most intertidal animals, the constant rising and falling of the sea eliminates the necessity of internal clocks. With their limited mobility, they don't need to anticipate the tidal cycle. They simply respond. When starfish, for example, are removed from the rhythm of the tide pools, their movements are totally random because they have no pattern to live by. The tide begins to withdraw. After the last splashes of water, the tide pools start to evaporate. A final wave passes over the barnacles. Now the intertidal animals are threatened by the drying sun. Many retreat to the bottom of the pools, which become warm and very salty. The sea hare is one animal that has no tolerance at all for the open air. It dries out quickly and dies. More mobile animals, such as crabs, are able to pull back to the ocean along with the tide. Fixed in their places, the barnacles and mussels are left behind. Yet these primitive animals are cleverly protected against dehydration. Inside their closed shells, each one guards a tiny bubble of water and air. The other danger of low tide is that predators can pick and choose at their leisure. Catching a limpet unawares, the seagull snaps it up before it can adhere to the rock. In most parts of the world, there are 2 low tides and 2 high tides per day. At night, the intertidal zone undergoes the same abrupt change in environment. A rush of water and activity, followed by a quiet period of waiting in the chill moonlight. Because the moon and the sun move separately, the 2 cycles they control, the tidal cycle and the daily cycle, do not mesh. This means that the tides never come at the same time every day. The fiddler crab is one intertidal animal that reacts to both of these cycles using a complex biological clock. These crabs are active at low tide, once during the night and again during the day. At high tide, they're buried in burrows under the sand. The tide is just now starting to recede, and at once a fiddler crab pushes away the wet sand and climbs out of its burrow. How did it know the coast was clear? The crab's clock is geared exactly to the tidal cycle. Even if it is taken far inland, the crab literally wakes up at the time of that day's low tide. Out of their burrows, the crab's first business is feeding. Only males have the characteristic fiddle claw, which is no help to them in this activity. With their other claw, they shovel sand into their mouths and scrape off the residue of algae and plankton. The crab then spits out the sand in pellets, which pile up to one side as it feeds. The behavior of fiddler crabs differs depending on whether it's day or night. They're most active during the days of the two lowest tides of the month. And this behavior, too, is controlled by an internal clock. 3 rhythms are involved here: the day-night cycle, the daily tidal cycle, and the monthly tidal cycle. The biological clock of the fiddler crab is somehow able to sort them all out. Well before the water has started to rise on the beaches, the fiddler crabs prepare their burrows for submersion. They haul sand and bits of vegetation to the entrance of their holes and then, crawling inside, close the hatch by pulling the sand over them. During their period of confinement, the buried crabs reduce their metabolism by 80%, virtually hibernating until the next low tide. Even the coloring of fiddler crabs is regulated by internal timing. At night they become paler, and during the day darker. The color change is determined by their day-night clock, but the depth of that change depends on their tidal clock. These are only the first discoveries about the complexity of animal clocks. A whole realm of nature's mysteries waits to be explored.